I have a big honor and pleasure to introduce our first speaker in the evening plenary session, Professor Rostislav Grigorchuk from Texas A&M University, USA, who will tell us about self-similar groups, joint spectrum, and renormalization.
Thank you. Thank you, Oksana. Standard procedure. Do you see?
Yes, great.
Okay. It full screen immediately.
Yeah.
Okay. Yes. Yeah, sorry, I'm not with tie as on those photo that was seconds before. It's a great pleasure and honor to deliver this talk during this wonderful conference. Usually Wednesday is a day when afternoon participants have a rest, but we work hard and that's good. Since the beginning of the last year, the world mathematical community demonstrated outstanding support to Ukraine and Ukrainian mathematicians. There are many examples of this, and in particular, the work on creation of the International Center for Mathematics in Ukraine is going on. There is a coordination committee which includes Masha Vyazovska, Fields medalist from Ukraine, now in Lausanne, Masha Vlasenko, Dmitro Savchuk, my former PhD student, Volodymyr Nekrashevich, who will be the next speaker after me, and many other mathematicians, and advisory board with such prominent mathematicians as Drinfeld, Ettinghoff, Exner, Skalsky, Scholze, Viana, and Zelmanov. Professor Vanderberg, at his plenary talk at first day of the conference, he mentioned the support for Ukrainian students, postdocs, young mathematicians that is arranged in Australia. So there are many examples of this sort. Also, I would like to mention that the role and popularity of Ukrainian language is tremendously increasing. Just as an example, in July 2022, last year, in the Institute of Henri Poincaré, Anna Erscher opened a conference using Ukrainian words. Several sentences were said in Ukrainian. And during this conference, we hear Ukrainian expressions, words. So all this is fantastic, important. And as the first day during the opening ceremony, the first conference was mentioned, which was initiated in Slovyansk. And the name of Kirichenko, Liman, Sushansky, Usenko were mentioned during that ceremony. I was at that conference. I remember it very well. It was fun, very pleasant, very nice time. And additionally to the beginning of this cycle of important conferences, also journal Algebra and Discrete Mathematics, the idea came and later was realized, and now journal exists, and everybody from this conference is welcome to submit article, good article, we expect. So this is introduction to my talk. Here, do you hear me, by the way? Do you see my screen?
Yes, we can see and we hear, and thank you for your
now
invitation.
You see a few articles related to the scope of my talk. So the beginning was basically in the first article with Bartoldi, whose name was mentioned yesterday in Gromov's talk. Then in my work with Nekrashevich, some important observations were made, and partly my talk will be based on them. The last one is a recent publication with Mikhail Lyubich, born in Kharkiv, Nguyen Bak-Dank, and it is published. So the title: So Similar Groups and Holomorphic Dynamics, Renormalization, Integrability, and Spectrum. So all this matches the title of my talk. I have many slides, and just let me briefly explain that there will be 3 or 4 parts. First will be a very quick introduction to self-similar groups. Then we will switch to kind of analysis, and we'll speak about joint spectra. Then classical tool known as Schur complement will be recalled, and its a modern interpretation by Volodymyr and me. Then I will discuss spectra of graphs and unitary representation, formulate few results, and we'll show several pictures of joint spectra, and we'll finish by some very recent results. So this is a goal, but because of a huge number of slides, I will sometimes make jumps, missing some slides, or very briefly explain. So self-similar group roughly is a group acting faithfully and in self-similar way on self-similar object. And so fractals could come to your mind, or many other objects which have self-similar structure, and you can think how group can act on such object in self-similar way. And after a few decades, we finally stop on the definition shown on the screen. Is a mouse visible? I don't have a mouse. I use a touch screen. Do you see a mouse moving along screen?
Yes, we see.
Yeah. So this is a definition which, for those who is not familiar, perhaps will be not very clear. But basically, a group is self-similar if there is alphabet on 2 or more letters, say binary or ternary or whatever alphabet, X, and we denote X star as the set of finite words over this alphabet, and group should act on X star on the set of words the following way. First of all, should not change the length of word. So the length of the word is preserved by this action, and then for each letter X in alphabet X, and for each element G in group G, there must be element Y in alphabet X and element H in a group G, such that for every word W of alphabet X, we have this relation written here. So G applied to word which begins with X, and then prefix W is a prefix. The image is Y followed by the image of W by the action of this element H. So G permutes elements of alphabet X in some way, and on suffixes it acts again as an element of the same group. This is the idea of self-similarity, and this element H will call section of element G at X. More convenient is interpretation of this definition that is the same as a group is self-similar if it has a faithful self-similar action by automorphisms of a D-regular rooted tree. D is cardinality of the alphabet, because we can identify, for instance, if alphabet is binary. Here you see a big picture of infinite binary rooted tree, and vertices of this tree are in natural bijection with binary strings. This is 0, this is 1, 0, 0, 0, 1, 1, 0, 1, 1, and so on. And those definitions translated translated in this language of action on the tree implies that the action is by automorphism. The root is fixed point, so vertices of the first level are permuted somehow, of the second level, and so on. And action preserves the structure of the tree. So a group is isomorphic to a subgroup of the automorphism of the rooted tree. And this group, the full group of automorphism, is uncountable group. It has natural topology, which makes it profinite group. We will not touch this. And what also is important that acting on the tree, it acts also on the boundary, delta t, which consists of infinite geodesic arrays joining a root with infinity. But again, viewing these geodesic arrays as infinite binary sequences, we get action on the space of infinite binary sequences for binary alphabet. And this space, again, in nature topology, is nothing else but just one of many realization of a counterset. So we also can say that similar groups are groups acting on counterset realized as a boundary of rooted tree, and action is in similar way. Now, another way to watch, to interpret all this is the following. So, G is so similar if there is a monomorphism, injective homomorphism from a group to the permutational Vries product of a group G with symmetric group SD. X again is our alphabet, T is cardinality, D small is cardinality of this alphabet, symmetric group X on the set X of cardinality D. And this Vries product is nothing else as a semi-direct product of this sort. So we have direct product of D factors, G, as D permutes them. And this is just another notation, another way to say that we deal with this permutation of Vries product. Now, so for each G, we have an element of this Vries product, which consists of D tuple of elements G1, GD against elements of a group G, followed by sigma, element of symmetric group. This sigma shows how element permutes vertices of the first level, and G1, GD are sections. These elements H, sections at vertices of the first level, first vertex, and so on, last vertex. And here, few examples of so similar groups. First of all, group generated by 4 involutions, and these Vries recursions from previous slides. So this replacement of G by this data, the D tuple followed by sigma, I now instead arrow right equality. Like this is the way to one of the possible way to define so similar group. We just write this what we call Vries recursions. So for instance, A permute sigma is permutation of 2 vertices of binary rooted tree, and sections are trivial, while B does not permute vertices because here we have identity element on the right. On the left section is A, right section is C, and so on for generators. Lamplighter, which this group was mentioned by Zellman on his talk, by Romo in his talk. Lamplighter group was mentioned in several talks, plenary and sectional. Hanoi Tower group X on ternary free is generated by free involutions. A, B, C. Then there is so-called Basilica iterated monodromy group of Z square minus 1 to generate group with these 2 recursions. All this group will play some role later. Alternative way to define so similar groups is we use the Mealy automata, mentioned for instance in the talk of Andrei Olin. So given non-invertible, non-initial Mealy automaton A, with input and output alphabet X and set of states, Q1 defines a group G generated by this automaton is a group generated by initial automata AQ, where Q runs through the set of states of automaton. So Q is element of Q. And a group of this study of groups of this sort was initiated by Ukrainian School of Mathematicians. First of all, Leo Kaluzhin, who also was a pioneer of these products, Glushkov in Institute of Cybernetics of Kyiv. He was the first, by the way, who rigorously, and his student Horch from Czech Republic defined groups generated by initial automata. Not in this way, but just you have a few initial automata, different automata, but initial with specified initial states, and you use a composition of automata as operation, and if they are invertible, you get a group. Vitaly Sushansky was one of developers of this. So here is an example of automaton which generates a Basilica group. It has three states, A, B correspond to generators. This corresponds to identity element. So we have like three generators, but one of them is identity element. And here is a brief description of how it acts on particular sequences, but maybe I will skip this. And now I go to the second part of my talk. It's a joint spectrum, spectrum. So now completely like different well analysis. Suppose we have a K tuple A1 AK of bounded operators in a Hilbert space H. We take any linear combination with the complex coefficients. Sometimes we consider real coefficients and denote this A of Z. Z is a K tuple of complex numbers. A joint spectrum, I denoted sigma J joint of this pencil, of this pencil of operator, is a set of points Z for which A of Z is not inverted. It's kind of similar to definition of spectrum of matrix, spectrum of operator. Only in that case we have two operators, operator and identity operator. Basically, and it's easy to understand that, and so spectrum is the set. So we consider expression A minus lambda identity element and look for the set of lambdas for which operator is not invertible. So here, homogeneous version of this and multivariate. And we do not assume in general that the identity element belongs to this tuple, but if it belongs, it's important case, the most important case, and it relates to the classical spectral problem to the spectral problem of finding and study joint spectrum of tuples of operators. Now, because this spectrum is homogeneous, if we multiply by scalar tuple of operators, if we multiply by scalar, a joint spectrum will not change. We can factorize by a non-zero complex number and get a subset in the projective space corresponding. So this is projective joint spectrum. So we can study joint spectrum or projective joint spectrum is equivalent. Okay, and now I got a problem. No. Yeah. Any question? And now definitions that can be criticized in certain way because like it is difficult to define what is a fractal, for instance. So I suggest to say that the spectral problem, and this is renormalization approach 1. I don't see if you see the title of because my screen doesn't allow to see the title of this page, but it's renormalization 1. So we say that the joint spectrum or pencil is renormalizable if there is a rational map, R denoted, from CK to CK of degree greater equal to such that a joint spectrum, which I denote now omega of this pencil A, is an invariant set for R. In other words, pre-image of omega is omega. And the map R is called a renormalization map. And using such approach, spectra of many operators coming from graph theory, Laplace operator, random walks, Markov operator, convolution operators in Hilbert space L2 on group, operators associated with unitary representations, for instance, regular, quasi-regular, Koopman, groupoid representation were computed. I will show a few examples. It was successfully applied to the spectral problem associated with many self-similar groups and is based on the use of the classical tool known as a Schur complement. Now, I briefly recall what is Schur complement. Let H be a direct Hilbert space decomposed finite dimensional or infinite dimensional, decomposed as a direct sum of two subspaces. M be a bounded operator, and M is presented by operator matrix A, B, C, D, where A, X is operator on H1, D on H2, B operator from H2 to H1, and so on. Now, definition assumes that that this operator D from H2 to H2 is invertible. Then M is sorry, it's not definition. It's not definition but statement. But yeah, so we assume that D is invertible. Now we consider expression A minus B D inverse C. So we use these elements to build this operator. It's operator from H1 to H1. I denote it as one, and it is called the first Schur complement. And the definition statement tells that M is invertible if and only if this new operator is invertible. So this is a statement. In similar way, you can define a second Schur complement and a similar statement. M, if A is invertible, M is invertible if and only if the second Schur complement is invertible. And in fact, one can define Schur complement for any decomposition of H as a sum of two or more subspaces. And here, inversion formula. So in case D is invertible, M inverse is given by this expression, which uses this S1 first Schur complement. And additionally, if dimension of the space is finite, and so we can use a determinant, like to determine is a matrix singular or non-singular. The determinant of a matrix M is a product of determinant of matrix D and determinant of a first Schur complement. Now, definition which you can find in my paper with Voldemar. Let H be now a separable infinite dimensional Hilbert space, D greater equal to D self-similarity of H is an isomorphism between H and direct sum of D copies of H. We know that all separable infinite dimensional Hilbert spaces are isomorphic, so certainly there is isomorphism between H and direct sum of finitely many copies of H, and not unique, and we call this similarity of on Hilbert space. So we started with self-similar groups. Now we are speaking about self-similarities of a Hilbert space, and observation from those articles tells that such self-similarities are in natural bijection with the star representation of the famous Kunz star algebra OD given by this set of generators and these relations. And there are many of them. of representation. So there are many dissimilarities. One concrete. So here, continuation of this theorem, more detailed information, but we will not need. And now I give again a definition that basically is in our article. Now assume H still is infinite dimensional, separable, decomposed as a direct sum of the subspaces. Each of them are infinite dimensional. We fix phi isomorphisms between Hi and H. And so psi built using this phi1, phi gives us dissimilarity on Hilbert space. Now, I define what I call covering Schur complement, but immediately switch to the name called Surmap. Is a map S tilde from the space of bounded operators on H to itself, given by this formula. So S1M is a Schur complement applied to the first summand, but we conjugate by this phi1 isomorphism in such a way that we get operator on H back. And so we get kind of universal Schur map on infinite dimensional Hilbert space, but it depends on psi. If we change, we can do this for any summand, but permuting summands, we always can put summand on the first place. So basically, we change just dissimilarity. So right now, I think I have defined important objects, basically never not studied yet. Schur map in the space of bounded operators on Hilbert space, infinite dimensional Hilbert space. It's homogeneous again, and so we can consider projective version of this map. And now, if we have a finite dimensional subspace E in the space of operators, say subspace of dimension K, which is invariant with respect to our Schur map, so we can induce this Schur map and on this subspace, and then get a map on the after projectivization, we get a map on finite dimensional projective space. And now I formulate three open questions. Describe finite dimensional subspaces of the space of bounded operators invariant with respect to S tilde, with respect to Schur map. Now, how previous problem depends on psi, and in what cases the restriction of Schur map onto this finite dimensional subspace is a rational map from CK to CK. Later I will. So basically, we have a bunch of examples of finite dimensional subspaces invariant with respect to the Schur map. We are very far from classification, and in those all examples, the corresponding map is the rational map, and this gives relation to holomorphic dynamics, to study of iteration of rational map. Multidimensional rational map like Fatou, the sets, and so on. Now, example of a dissimilarity. We go back to a regular tree, the regular tree, and the boundary of the tree, as I told, is a Counterset. It has a natural decomposition as the joint union of pieces corresponding to vertices of the first level. Each subtree with the root at first level is canonically isomorphic to the whole tree, and from this we get natural. On the boundary of the tree there is a uniform Bernoulli measure denoted mu, which is invariant with respect to all automorphism of the rooted tree, and so we have Hilbert space H L2 on the boundary with respect to this measure, and we have this dissimilarity coming from tree structure. Now, When we have a probability measure space x mu, so mu probability measure on space x, and group action, reaction of group G on X by measure preserving transformation, then Koopman representation pi of G in Hilbert space is a unitary representation given by this formula. So operator pi of G, G is element of a group, applied to function f, evaluated at point X, is just f evaluated at G inverse X. It's unitary representation, and we apply this for a group acting on the root E3 with X boundary and nu a uniform Bernoulli measure. So with each self-similar group, we can associate this representation. We denote it pi. Now, if we have any representation, Koopman, or regular or quasi-regular, any unitary representation, and if we have an element M of a group algebra, so the linear combination of elements of a group with some complex coefficients, then we can build operator M, which is application of representation to M. So when we replace each element by corresponding operator, we call this Hecke type operator. They are not classical, but we use this terminology. And we can do this not only for Koopman, but as I told, for any unitary representation. Now, in the situations that we deal with, and now I have to accelerate because time runs very quickly. We have situations that our Hilbert space H is a union of increasing sequence of subspaces Hn. Hn is a finite dimensional subspace of dimension d to the power n. It corresponds to level n of the tree. There are d to the power n vertices on d regular root E3. And H is closure of union of these finite dimensional subspaces. And these subspaces are invariant for Koopman representation. And then, and therefore, spectrum of operator M is nothing else as a closure of the union of spectra of this reduction of operator M on these finite dimensional subspaces. So now Mn like are finite dimensional matrices. We compute eigenvalues of them, take union, and follow by closure. In such way, we get spectrum of our operator M. This expression is nothing else as a characteristic polynomial of matrix M. And so I like go back to the pencil. Now I assume I have a set of elements of a group. I take linear combination of them with complex coefficients, so element of a group algebra. I replace generators. I assume that they are generators, this A1, AK. I replace them by corresponding operators of Koopman representations, so I get pencil of operators. But now I do the same for finite levels of the tree. So instead of infinite dimensional operator, I consider matrices Mn of dimension d to the power n. I consider characteristic polynomial of them. Z is multivariate parameter, lambda is spectral parameter, and Qn is determinant, so characteristic polynomial. And in situation that we study, we have the following relation, roughly, that determinant corresponding to level n plus 1 is equal sum to the power d to the n of some concrete function f, followed by determinant of previous level, but evaluated not at point z lambda, but at point r of z lambda, where r is certain rational map from the space of dimension k plus 1 to k plus 1. So r is again a renormalization map associated with our spectral problem. So here I discuss briefly renormalization approach 2, but both of them match in fact. And so in situations that we were able to apply this approach, our spectrum comes as follows. We begin like from level 0. Characteristic polynomial in this case is just a linear function. So when we equate 0, we get hyperplane, and then we have to take, which I denote U, and then we have to take preimages of this hyperplane, all preimages using renormalization map R and union and closure. And this will give us a joint spectrum. Joint spectrum. If we apply this to the group of intermediate growths, that was the first example, this recursion can be transferred into matrix recursion, shown here. And if you take a pencil linear combination of generators A, B, C, D, and identity element, which is I, and replaced by corresponding matrices, we will get matrix of this sort. And in this corner, we see that generator A, all generators A, B, C, D are involution. So here we have involution A in some scalars, and here we have free involution C, D, B, but they commute, they generate Klein group. So we can easily determine for which values of parameters this corner is invertible because A in involution, and for which is this invertible. And so we can apply this Surmap that I discussed, and we will get first and second Surmaps from C5 to C5, and the first one is this map, second one is that map. And what we know is that joint spectrum is invariant set of these maps, and in some degenerate direction, we know from the time of my paper with Bartoldi that joint spectrum is an interval or union of two intervals, while for the majority of direction, it is a counterset of Lebesgue mesh 0. And the latter result is based on the joint wave with Lenz and Agnibida, and is based on the use of substitutional dynamical systems and the reduction to random Schrödinger operator. If we equate three parameters, then we get simpler maps shown here, and they are quite degenerated, as was mentioned by famous people in holomorphic dynamics. They are semi-conjugated to Chebyshev map, and this is a picture of a joint spectrum, joint projective spectrum, in this simplified version. So here, the real spectrum of operators that we are interested in, when we cross by horizontal line, we get, in most cases, we get union of two intervals. And here is an example of this recursion level n+1, how it depends on determinant of previous level. Okay, my time is basically expired, as I understand. But okay, a few more minutes, I hope Oksana give me. Yes, Oksana, or no?
Yes, you have 4 minutes.
4 minutes. So this is also applicable to spectra of graphs, regular graphs, Cayley graphs, Schreier graphs. Spectra of graphs were mentioned in talk of Alex Lubotsky. Cayley graphs were mentioned in many talks. This is Cayley graph of group of intermediate growth, Schreier graphs of group of intermediate growth, Schreier graph of Hanoi. Definition: what is Markov operator, normalized agency operator, whatever. Among measure question is what could be the shape of the spectrum of a regular graph or Cayley graph of a group? Can a torsion-free group have a gap in the spectrum? If yes, then we get a counterexample to the Kadison-Kaplansky conjecture on idempotence. With Bartoldi, we show that there are Schreier graph with counter set as a spectrum. But if a group, if a Cayley graph can have a counter spectrum, is not known. This slide is combination of different results showing that, for instance, for Lamplighter group, a Vries product of group of order 2 and infinite cyclic group, for some system of generators coming from automaton representations, the spectrum is pure point spectrum, consists of only of eigenvalues, while Point C tells that for another system of generator, it is continuous, no eigenvalue. So change of set of generators can tremendously change spectral properties. Famous question of Mark Kaskin, one here, the shape of a drum, was asked, okay, in case of the remaining manifolds or whatever, people ask in case of groups. With Artem.co, we showed that answer is no in very strong sense. For uncountable family of groups of intermediate growth, for generated for involutions, the spectrum is the same, while Kelly graphs are not only not pairwise isometric, but even not pairwise quasi-isometric, much weaker equivalence relation used by Gromo and his followers. And this notion is the base of the geometric group theory now. Random graphs, density of states. One more theorem with Artem.co, who is now in Warsaw, very impressive theorem, but I have no time. So last slides with Zoran Sunik, we study Hanoi Tower groups given by this automaton. The corresponding Surmap is presented here. This is the picture of a joint spectrum in this case. In this case, if we cross by horizontal line, we get a Counterset. So example, such shape. This is an example of iterated monodromy group of polynomial z square plus I is the square root of -1. We have three-dimensional map. We studied the group in details, but this is approximation picture of joint spectrum. We were not able to compute it completely. And final slide, iterated, the theory of iterated monodromy groups was developed by Vladimir Nekrashevich. Basilica was discovered by me and Zuk. It's iterated monodromy group of this polynomial. The corresponding map is this one. It's not complicated map, but very not looking not complicated, but dynamics is very complicated. And the last result tells us that the density of states associated with Schreier graphs of the Basilica group is an atomic measure whose support is a Counterset of positive Lebesgue measure. And this is like a new feature because in all previous examples, in case when the spectrum is Counterset, it was a set of Lebesgue measure 0. Дякую вам за увагу.